We are very happy to have Geoff, and he's a new faculty at UC Berkeley. And he will tell us about the leading order correction to the QES prescription. Please start.
Okay, thanks very much. So yeah, I feel I should say that I'm very excited to be joining Berkeley, and for everyone that I sort of haven't got the chance to meet yet, I'm sorry that everything is remote currently, and yeah, feel free to like email me or whatever if you want to say hi at some point. But yeah, hopefully, at some point in the not too distant future, we will all be able to hang out in person. Okay, so this is some work with Chris Akers that hopefully should be coming out very soon, sort of in the next few days, theoretically. So few is a very flexible term. And it's on leading order corrections to the quantum extremal surface description. Okay, so very boring first slide. ADS-CFT, as we all know, is a duality between conformal field theory on the boundary and quantum gravity in asymptotically anti-de Sitter space in the bulk. So in this diagram, these fish are all the same size, right? They seem to get small towards the boundary, but really they're the same size, and the circle is just infinite. So one of the big aims with ADS-CFT is this mysterious magical thing, is we want to understand the dictionary that relates objects on the two sides. And one very central element of the dictionary in its original form is what's called the Reattacchi-Nagy formula. And this basically says that if you look in your boundary theory and you look at just part of the boundary, so this region big B, and you look at the reduced state of that region, then leading order, the entanglement entropy of that region is given by the area of the minimal bulk surface anchored on that boundary, divided by 4 times Newton's constant. So this is sort of the original version, but what we've seen over the decades since, particularly due to Faulkner, Lukowitz, and Madisina, and then Engelhardt and Wall, is that really this prescription needs to include quantum corrections. And basically what those quantum corrections are is that we should replace this area over 4G Newton by area plus the bulk entanglement across the surface. So together these make something called the generalized entropy. But really all this means is that if this blue fish here is entangled with this blue fish here, then the entanglement between the two, because they're get entangled across this red surface, contributes to the von Neumann entropy of the boundary. Okay, and yeah, really, it doesn't have to be entanglement. Really, any bulk von Neumann entropy in this whole region, called the entanglement wedge, contributes to the boundary entropy. Okay, so this formula can be derived from the gravitational path integral. That derivation uses some assumptions that are going to be pretty key to my talk today. That started with Lukowitz and Madisina and a lot of people since. And it's had a number of successes, in particular, led to a derivation of the Page curve for an evaporating black hole. But really the focus of this talk is going to be showing that if you just naively apply this quantum extremal surface description without thinking at all about the states that you're applying it to, then you get paradoxical results. And in fact, these paradoxes already exist at leading order in Newton's constant. So it's not like you could imagine sort of, this prescription is basically right, but there's some tiny little corrections that are needed to fix everything up and make it work. Yeah, they're really already there at the leading order. You need qualitatively important corrections to fix it. So you can actually see these paradoxes in calculations that involve quantum extremal surfaces and evaporating black holes and islands and stuff. And you can get results using the naive quantum extremal surface prescription that are inconsistent with unitarity for certain things you might want to calculate. But they also show up in states that don't involve any black holes at all. The good news is that if you do more careful entropy calculations, using the replica trick, then you actually get results that are not paradoxical, consistent. And the results show, these calculations show why the assumptions in the traditional Lukowitz-Maldacena style derivation of the quantum extremal surface description breaks down. And I wouldn't say it's completely intuitively clear why the assumption breaks down sometimes and doesn't break down other times, but you can see it failing. You can see that you do this more careful calculation, it gives a qualitatively different answer. And so instead, what you find is that the naive quantum extremal surface prescription needs to be replaced by what we call a more refined version of the prescription, which involves these new quantities called smooth min and max entropies, which are concepts from what's called one-shot quantum Shannon theory. Really, like the quantum Shannon theory is the information-y part of quantum information theory, and one-shot quantum Shannon theory is doing quantum information when you only have one copy of a state rather than a large number of copies of the same state. So that's what we have in ADS-CFT, so it shouldn't be too surprising that these things appear. And in fact, all the results we're going to find, and in particular what they have to say about entanglement wedge reconstruction, are very, very closely related to a thing from one-shot quantum Shannon theory, a task from one-shot quantum Shannon theory called one-shot quantum state merging. Okay, so that's a basic preview of what we're going to talk about, but I'm going to start very simple and just talk about why there's a paradox if you just heedlessly apply the quantum extremal surface description without thinking about what you do. And the setting I'm going to do this in, so as I say, you can see it in all sorts of different settings, is a setup that goes back to a paper by Akers, Leichenauer, and Levine from last year, which is just dust balls in ADS3. Okay, so we're going to consider a boundary region B in ADS3 CFT2 that's just going to consist of two regions, right? So we have this region on the bottom and we have a region on the top. And this gives us two classical and also quantum extremal surfaces that just have different topologies. There's the one that just sort of is homotopic to region B, and there's one that's homotopic to region B bar, but both of them satisfy the homology constraint, both of them valid extremal surfaces. Okay. Now that's all true in vacuum, ADS3, but what we can also do is we can add some matter. Specifically, we can add matter with an order epsilon over g Newton energy, where epsilon is small, but it's order 1. And that's going to give some back reaction on the geometry, but the back reaction is going to be order epsilon, because Einstein's equations have a Newton's constant in them. So the geometry of this thing is going to look very similar to the geometry of the ADS3 vacuum. If this matter is in a thermal state, then the entropy will be comparable to its energy and will also be order epsilon over g. So small, but the same parametric order in g Newton as the area terms. So now what we can do is we can just tune the size of this region B so that it's really quite close, has greater than epsilon precision to the transition point where B is half of the entire boundary and where the two areas are equal. And if we do this, then we can set things up so that sort of this area 1, that's homotopic to B bar, is smaller at leading order than the area 2 over 4g Newton. But area 2, which is the one homotopic to B, is itself smaller than area 1 plus this thermal entropy S. Okay. So now we're ready to have a paradox. We just consider 3 states. Our first state is going to have, all this matter, all this energy, just be in some typical pure state. Okay. We can then look at the generalized entropies of the two surfaces. And what we find is that this, we don't have any von Neumann entropy here. It's just in some pure state that maybe be thermodynamic entropy, but not von Neumann entropy. So the minimal generalized entropy surface is the surface gamma 1. And the generalized entropy is just A1 over 4G Newton, plus maybe some order 1 correction just from vacuum entanglement. What about if the matter's in the thermal state? Well, now the generalized entropy of the surface gamma 1 has this additional contribution from all the thermal entropy sitting in the middle here. And we set things up so that that is actually bigger than the generalized entropy of this other surface. So there's a phase transition, and now the generalized entropy is given by A2. Great. Final step to get our paradox is we're just going to take order 1 mixture of each of these two things. Okay, so now our bulk state is going to be some order 1 probability of being pure plus some order 1 probability 1 minus p of being thermal. So the quantum extremal surface says we've got to look at the two generalized entropies and take the smaller one. So the generalized entropy of this surface gamma 1 is again area 1 plus entropy of this thing, which now is just 1 minus p times the thermal entropy, plus some small order 1 maybe correction from an entropy of mixture term. What about the surface gamma 2? Well, it's again just the area term, so its entropy is just A2 over 4G. So the quantum extremal surface prescription, if we just applied it naively to this mixture of two states, would give this answer. It's just the smaller of these two things. So we tune P, then if we start with sort of P equals 1, and then start decreasing P, then the entropy will get bigger and bigger as we have more entropy in the bulk, and then it will reach a point where it saturates, and then it will just stop getting bigger. Okay. However, it is a well-established fact. Yeah, so if we look at this actual boundary state on B, then the global boundary state is going to be just a linear mixture of the pure and thermal states. Partial trace is linear, so that's also going to be true of the reduced state on B. And it's a standard fact about the entropy of a mixture of two states that up to some small order 1 correction, the entropy is just given by the expectation value of the two entropies in the mixture. So in this case, it's P times the entropy area 1 from up here, plus 1 minus P times area 2. Okay, and it's just a fact that these two answers are just totally different at leading order. Okay, so if we want to have a linear map from bulk to boundary, which we certainly should in this situation, there's no black holes or anything, then one of these three states, the quantum extremal surface prescription has to be giving the wrong answer at leading order. Okay, so I claim...
Geoff?
Yep.
Sorry, can you just go back to the previous slide?
Yep.
It just went really fast. So one thing that I didn't process is the role of the phase transition in the example where we have a mixture of the two.
Yep.
Is the point that it doesn't really matter where the phase transition happens in terms of as we dial P, because either way, these are just completely different expressions?
Yeah, exactly. Yeah. Yeah. So yeah, imagine we've just made P like kind of small, so we haven't got past the, well, let's imagine we're on this side of the phase transition, right? So A2 is smaller. Then this one's A2, and this one is P times A1 plus 1 minus P times A2. These are just different things, right? I can make P be order 1 thing and still be on that side of the phase transition. Similarly, on this side, this thing is giving A1 plus 1 minus P times S. This thing is giving basically A1 plus 1 minus P times the difference between the two areas. But we set things up,
the formula
so S
you
is
wrote
bigger than.
Sorry, yeah, but the formula you wrote down for S of B, the bottom formula for S of B assumes that you're on a particular side of the phase transition where the matter is included.
No, the
in
bottom
the
formula
entanglement,
does not make any assumptions. The bottom formula is a mathematical consequence of the fact that we have a mixture of these two states, and these two states have entropies A1 and A2.
I'm sorry, I thought that B is a boundary region, and the mixture of the states is only relevant if the
the partial trace is linear. So if we looked at the global state, we would have a mixture of the two states. Now we do a partial trace, and we still just have a mixture of the two reduced states.
I'm confused how P can matter if the matter ball is not in the entanglement wedge of the region B.
So according to the quantum extremal surface prescription, it seems like it doesn't. But this bottom equation, like, you know, if your boundary state is really a linear mixture of the two boundary states, which it should be if our bulk to boundary map is linear, then this bottom equation is just true. I can give you a proof if you want. It's not a very hard proof.
I mean, usually isn't the mixture, like this mixing entropy, just a bound on what the entropy is? But I guess you're making some further assumptions.
So there's an upper bound and there's a lower bound. The lower bound just comes from concavity.
It just differs by the Shannon term.
Yeah, exactly. And the upper bound has the Shannon term, but the Shannon term is like at most 1. So we have a lower bound and upper bound that differ by 1.
Yeah, thanks.
In answer to your question of why this can happen when it's outside the entanglement wedge, Raphael, the answer is that it's not really outside the entanglement wedge. And actually, when you consider this mixture, then this whole central region is sort of half in the entanglement wedge, half out. There's not a like clearly defined entanglement wedge.
Yeah, I think that helps. Thanks.
Okay, cool. Okay. So yeah, I claim that the one the QIS prescription is failing for is not the thermal state or the pure state. It's the mixture of the two. So why might we expect that to happen? Well, if we have some thermal state that involves a large number of degrees of freedom, then formally the rank of that state is infinite. Say for a simple harmonic oscillator, it would already be infinite. Same is true of a large number of simple harmonic oscillators. But we can approximate it to a very high accuracy by a state where we sort of project out all the eigenvalues that are much smaller than e to the minus s. So we can approximate this state by a state that has rank e to the s plus some subleading correction. This is really just the law of large numbers. This thermal state gets dominated by sort of typical states from the thermal distribution. So there is a formal quantum information way to restate this claim, which is just the smooth max entropy of this thermal state is approximately equal to the von Neumann entropy of the thermal state. So this is really just a restatement of the line above. The smooth max entropy, by definition, pretty much, it's the log of the rank of the smallest rank state that approximates your original state. Okay, so in the line above, we said we can find a state close to the von Neumann entropy, to the thermal state that has rank e to the s plus subleading thing. Another way of saying that is that the smooth max entropy of the thermal state is equal to S, the von Neumann entropy, plus some subleading thing.
Are you going to explain this in a little more detail, how well it has to approximate the state? Or it won't matter here?
For the moment, I mean, how well it approximates, the smooth max entropy is parameterized by an error epsilon. Okay, so it's labeled by some epsilon that tells you how well it needs to approximate the original state. So if I change epsilon, then the smooth max entropy will change. But for most of the things you care about, it doesn't change too much. The dependence on epsilon is not too horrible.
But you're saying you can't take epsilon to 0?
If you really took epsilon to 0, yeah, then for the thermal state, for example, it will become infinite. In practice, we're going to want epsilon to be sort of polynomially small in G Newton, but not exponentially small. Yeah, I'm going to avoid talking too much about epsilon because it makes the whole thing much messier, and that's one of the sad things about smooth entropies, that you sort of need these epsilons. You get all these equations relating different smooth epsilons, and there'll be smooth entropies, and there'll be different epsilons in all of them, and they'll all be bounded in each other in different ways, and it gets kind of horrible. But in practice, you can sort of forget about it.
Does that, this epsilon is just a general thing you need for statistical mechanics? Because it's a density, right? You need a width. Is that something different?
Yeah, exactly. It's
same thing, right?
It's just like the fact in the law of large numbers, right? Everything gets dominated by some tightly peaked Gaussian, but here you've got to, if you want to put it like an upper bound and lower bound, then you've got to have some epsilon cutoff where you say just forget about
epsilon is exponentially smaller than you're picking a pure state anyway. So
exactly, yeah, exactly.
Yeah.
By considering exponentially small probabilities, then you can break the typicality. Okay, so this is also true for the pure state. The smooth max entropy and the von Neumann entropy are the same. This is just because the pure state itself has rank 1, so clearly we can approximate it by rank 1 state, and then log of 1 is 0, so they're both equal to 0. But if we think about this sort of mixture of the two, then if I can approximate the mixture of the two, then I can in practice also approximate the thermal state. Because I can just take my approximation to the mixture and then subtract away the pure state, rescale, and that will have to be an approximation of the thermal state. So what does that mean? It means that the smooth max entropy of this mixture is the same as the von Neumann entropy of the thermal state, which in turn is related to the von Neumann entropy of the mixture by S over 1 minus P. Right, so the smooth max entropy of this mixture is much, much bigger than the von Neumann entropy. So in general, these large corrections are going to be able to show up whenever you have these sort of incompressible states, where sort of the number of degrees of freedom, number of qubits you need to encode the state is bigger than the entropy, that they can't be compressed down to S qubits. Okay, so that's going to be sort of the heuristic story we'll find. I'll give a much more precise statement of the rule we want later on. But before I do that, I'm just going to show for this specific simple example how when we actually do the replica trick properly, we don't find the naive quantum extremal surface prescription answer. We find the self-consistent answer. Okay, so let me very briefly introduce the replica trick. So what is the replica trick? It's a trick for calculating von Neumann entropys using a path integral. So the von Neumann entropy is minus trace of rho log rho. Log rho itself is hard to compute using a path integral. So what you do instead is you compute trace of rho to the n using a path integral. And then you take log of that, divide by 1 minus n. This gives you something called the Rayleigh entropy. And then you take that answer as a function of n, you analytically continue it to n equals 1. And in the limit n goes to 1, this formula, using L'Hopital's rule, gives you the von Neumann. Okay, so that's a very brief introduction because I think most people will be familiar with it. So how does this apply in ADS-CFT? Well, how do you evaluate trace rho to the n in ADS-CFT? The first thing you do is you note that your sort of states, your bras and your kets are prepared by Euclidean path integrals. So if we're having n copies of rho, we're going to have n bras and n kets. So we're going to have sort of 2n Euclidean path integrals at this point. And yeah, so sort of for a vacuum state, for example, it's just prepared by Euclidean path integral in the hemisphere. We want to stick some matter in here. We'll have some boundary conditions for the matter that create the matter. And if we want it to be a mixed state, then we're going to correlate the boundary conditions between the ket and the bra. Okay. So then we want to look at the trace of the reduced state to the power n. So we've got to do a partial trace over everything else. So what does that mean in the path integral? It just means you take the boundary conditions on the bit you want to trace over and you just glue them between the bra and the ket. And we're going to do that in all the n copies. So now we're going to have sort of n spheres with cuts cut out of them. okay, that are the reduced density matrix. Then finally, to get trace of rho to the n, we need to glue everything together. But because it's trace of rho to the n, not trace of rho all to the n, then they get glued together in a cyclic way. So this ket gets glued to this bra, this ket to this bra, and so on, and then eventually this ket gets glued back to this bra. Okay, so eventually you end up with sort of just one boundary with everything glued together, and that's the number that is trace rho to the n. So that's sort of how you would do the boundary path integral. What we're really going to do is bulk path integral, and the claim of ADS-CFT is that the boundary path integral is equal to the bulk path integral, where we integrate over all bulk geometries that have the boundary conditions, have a boundary given by the boundary in the boundary path integral. Because we're going to take Newton's constant to be very small, then this bulk path integral is going to be dominated by saddle points. Okay, so in general, sort of finding all the bulk geometries, all the saddle points with the correct boundary conditions is a hard thing to do. So to make things simpler, we're going to consider a particular class of states called fixed area states, which were introduced by Chris and Pratik and Donghala and Marolf a year and a half ago now. So what are these states? They're just states where you prepare the state using a Euclidean path integral, but then you just measure the areas of all the extremal surfaces. How does this help? It means that the path integral no longer integrates over the areas of those extremal surfaces. And so saddle points, when we do the path integral, can have conical singularities that sit at these extremal surfaces. This is just because the sort of conical deficit or excess is the conjugate variable to the area. And so it can have a discontinuity because you've measured the area. What does this end up meaning? Well, the beautiful answer is that the saddle points that you get basically just look like the original bulk geometry, except you have branch cuts in the bulk where different sheets of the bulk, you have these n copies, n sheets of the bulk, get glued together. And they get glued together in different ways with branch cuts at the extremal surfaces. And those branch cuts create conical singularities, because when you go in a loop around the branch cut, you end up on a different sheet. So you maybe have to go around several times before you got back where you started. So the circumference is not equal to 2 pi r. It's equal to something larger. So you get a conical singularity. But otherwise, the bulk geometry just looks like the original sort of n equals 1 bulk geometry. And so that's really great, because when you sort of normalize this trace rho to the n, then you've got to divide by n copies of the original n equals 1 geometry. So that means all the gravitational action just cancels out between the numerator and the denominator, except for the contributions you get from these conical singularities, which just give you a factor of the conical excess angle times the area of the surface divided by a pi g. Okay, so what do these saddles actually look like? Well, they've got to match the boundary conditions of our boundary path integral. And remember, the boundary of this region, big B bar, we glued directly onto the sort of same bra, right, without any permutations. So that means in the bulk, similarly, this region near region big B bar has to be glued onto the corresponding bra without any sort of permutation applied, any twists between the different sheets. Similarly, region big B got glued onto the bra that was like cyclically permuted around the n copies. So that means the region in the bulk near region B also has to be glued in a cyclic fashion like that. This tau I'm going to use to represent the cyclic permutation that just takes 1 to 2, 2 to 3, and so on. Okay. But this sort of middle region does not have any boundary. So by adding branch cuts at these extremal surfaces, we can have it basically be glued to any bra that we want. We can glue in an arbitrary permutation pi. Okay, so we could say glue sheet 1 to sheet 5, sheet 2 to sheet 4, sheet 4 to sheet 3, you know, however you like in some complicated permutation. Did someone have a question? Okay.
I'm sorry. I'm sorry. I didn't muted it. I'm very sorry for the interruption.
Okay, no problem. Okay. So each of the permutations pi gives us a different saddle point. And in principle, the right thing to do is just to sum over the saddles associated to each permutation. So you can do that because the gravitation reaction is so simple. All you get is this formula where we sum over each of the permutations. We have a gravitational reaction that just comes from these conical singularities that depend on the permutation. And finally, we get a sort of bulk action that just comes from the fact that you have the bulk state rho here, and you have bras and kets, and you're gluing them together with different permutations on different regions. Okay, don't worry too much about the details of the formula now. But the key point is that we have all these saddles. Some of them are going to give a larger contribution than others. And if we just dropped everything except the leading saddle, which will either be the permutation identity or the permutation tau, depending on sort of which side of the phase transition we're at, then we just have a formula that doesn't have this sum, and it's just some function that's roughly analytic in n. And we could then analytically continue it and get an answer for the von Neumann entropy. But the answer we would get would be the naive quantum extremal surface description, which we claimed was paradoxical and wrong. Okay, so that's the sort of traditional thing people do is just drop everything except the leading saddle and then analytically continue that saddle. I call it the Lukowitz-Maldaceno assumption. It's originally introduced in their paper. But that's giving us the wrong answer here. So we're going to be more careful. We're going to try and keep this full sum and see what happens.
Geoff?
Yep.
Sorry, just on the previous slide, what do you mean exactly by so by keeping the leading saddle, you just mean that you completely ignore the fact that you're allowed to have these arbitrary permutations in the region?
Yeah, exactly.
Pi.
So the largest contribution in general will come from either the permutation identity or the permutation tau. Just as a general rule, this is true.
But it's not leading in the sense of some expansion in G Newton, right?
Well, it has the smallest action, so it gives. It's not leading in terms of orders of an expansion.
Mm-hmm.
By leading, I just mean maybe I should have said dominant rather than leading. Would that have been clearer? But regardless, the point is, if you just keep the identity or you just keep tau, then you get the naive QIS description. Okay.
Jeff, one more question.
Yep.
That those naive saddles, they're leading for integer n. Is that the idea? But they're not going to be leading near n equals 1. Is that going to be the punchline?
So for non-integer n, you don't have a sum over a finite number of saddles. One way to see this is like you have a different number of finite saddles for different values of n, right? So you only have a simple sum over saddles for integer n. And if you go to sort of n equals 1 plus epsilon, say I kept both the identity and tau saddle and tried to drop everything else, right? And then I took n goes to 1. Then my limit n goes to 1 is just totally wrong because I end up with 2 saddles when I only actually have 1 saddle with n equals 1. So the saddles have all got to merge together. So the lesson isn't going to be that a different saddle dominates. It's that you can't think about a single saddle for non-integer n when you don't have this simple situation where one family of saddles dominates.
All right, thanks.
Okay. So yeah. So we have this formula for tracing rho to the n, but actually we can drop some of the terms in it. So these things I've written C pi. That's really the number of cycles in the permutation pi and the permutation tau inverse composed with pi. So those show up just because they control the amount of conical excess that I have, and so the gravitational action I get. And the thing to note is that these areas A1 and A2 are divergent, they're infinite. The difference between them is finite, but each of them individually is infinite. So any saddle that doesn't maximize the sum of these two numbers of cycles is going to be infinitely suppressed. So we can just forget about it and drop it completely. So the remaining permutations that you're left with are in one-to-one correspondence with something called non-crossing partitions of the bulk of a disk. I'm going to call them non-crossing permutations. So they're the ones that we need to not forget about. And so what we want to do is we want to take this formula and we want to just analytically, where we only sum over the non-crossing permutations, and we want to analytically continue the formula as a function of n. And the big problem here, which is what I was saying to Ahmed, is that the number of terms in the sum depends on n, right? So it's not clear how to turn this. Each of the individual terms in the sum is an analytic function of n, but it's not clear how to sort of turn the full sum into something that's analytic. Fortunately, there's some technology that was developed for the theory of free probability, basically random matrix theory, that lets us do this. And I'm not really going to talk about it in detail because it was all done in my paper from last November on replica wormholes with Jembin, Yang, Douglas Stanford, and Steve Schenker. But basically the way it works is the following. You look at this quantity called the resolvent, which is just defined as the trace of the inverse of lambda minus the density matrix. Lambda here is just a number, so this is just a function of lambda. And by a Taylor series expansion, what we can see is that this thing is just determined by the trace of rho to the n, okay? So if you know trace of rho to the n for all integer n, you can work this thing out, in principle at least. And it's easy to see as well that the sort of density of eigenvalue distribution of rho is determined by the imaginary part of this resolvent. So if we can compute this resolvent, we have all the data we need to get the eigenvalues of rho and hence to get the bond nominator. Okay. When you put in, you take the results for trace of rho to the n, just the particular formulas you get for our particular mixture of a pure and thermal state. You plug that into this technology for getting resolvents out of that sum, for sort of doing this infinite sum and turning it into a recursion relation. You magically get this formula, okay? I'm not gonna go through the details because it takes a while, but you can see it in the paper from November or in my paper in CRIS when that comes out in a few days, hopefully. But the key point is that this is just a cubic equation that this resolvent equation will satisfy. And cubic equations have a general solution, so you could just solve it. But it's also the case that no one ever got any insight out of using the general solution to a cubic equation, so you should never do that. What we can do instead is do what you always do in physics and make some approximations. So in particular, we can notice that we have this very small number in front of this factor of r, and we have a very big number here, okay? So if r is not too big, we can just drop this term. That then means we just have a over e2, a to the e2 here. And then when we multiply out the denominators, we just get a quadratic, okay? And quadratics, the formula is an awful lot nicer. We can solve it. Similarly, if r is really big, then it will become so big that this number is much bigger than this number, and we can drop this term as sufficiently large r, okay? And the key point is because this term has a s in the denominator, and this one does not, there's a large overlap where both the approximations are simultaneously valid. Okay? So what we find is that making either approximation, we get a quadratic equation. And those quadratic equations have overlapping regimes of validity, and they let us get the whole solution with high accuracy. So whenever you have a quadratic equation, the solution is imaginary, has an imaginary part, if and only if the discriminant is negative. And what you find is that that happens, there's sort of one region where that happens for each of the two approximations. And so you get a final answer for the eigenvalue density that has two peaks. They're two narrow little peaks with this sort of a semicircle distribution over the peak. So one is that you get a load of eigenvalues that have eigenvalue p over e to the a1. So these are the eigenvalues that come from the pure state in the mixture, right? If I had a pure state, I'd have all the eigenvalues would be roughly e to the minus a1. And we have p probability of that. And so that gives us all these eigenvalues. And then we have all these other much smaller eigenvalues that are like e to the minus a2. And so they're the ones that come from the thermal state, right? The thermal state, all the eigenvalues are e to the minus a2. And we have, 1 minus p probability of getting them. So yeah, all these other eigenvalues have eigenvalue e to the minus a2. So we've got a sensible entanglement density. And from here, it's really trivial to just integrate over this. And we get an answer for the von Neumann entropy that is indeed exactly what we claimed we should get. Okay, so just using this resolvent magic, we get the right sensible answer instead of the naive quantum extremal surface. So yay, that's great. But that's just one particular, random choice of state to consider that sort of happened to let us use this free probability technology. What we really want to know is if I just have some arbitrary state, when does the naive quantum extremal surface prescription apply? When does it not, right? When do we need to use some other rule? So that's going to be what I'm going to talk about next. So the sort of bad news is that if I just have some arbitrary, like entangled bulk state where, I have some arbitrary tripartite bulk state on the three regions, the one near boundary region B, the one in the middle, and the one near boundary region B bar, then we just don't have any tools, even for fixed area states, that will let us do the replica trick calculations explicitly. That will let us do this analytic continuation, or like resum it and get the resolvent or anything like that. But you can do something else instead, which is kind of cool, which is you can just note that the formula we get for trace of rho to the n, at least in fixed area states, is exactly the same formula that you get in a particular random tensor network. Specifically, it's this random tensor network I've shown here, where you sort of have some random isometry from the region in the middle, little b bar, little b prime, right? It's the region between the two surfaces. And then that maps to two legs, one of which has dimension e to the a2, the other has dimension e to the a1. And then you take those outputs, you add in the stuff in little b and little b bar, i.e. sort of the outsides of the two extremal surfaces, and then you just apply some unitary to them, which honestly doesn't do anything to the entropy. Right, and then this just gives you big B, and this gives you big B bar. So this is exactly the sort of tensor network you would make if you were trying to construct a sort of toy model of this RT phase transition with a tensor network based on all our intuition. But magically, you can just evaluate trace of rho to the n for this tensor network, and you get exactly the same sum over non-crossing permutations with exactly the same terms. In each term, the sum is equal that we got in gravity. Okay. So how does this help us? It means we can do a really dodgy cheat and work out what the replica trick calculation must give us the answer for the von Neumann entropy by just calculating the entropies in this tensor network by any technique we like like not using replica tricks or anything like that, just using the fact that we know a lot about tensor networks and finite dimensional quantum systems, a lot more than we know about gravity, and just work out the answer in the tensor network, or at least work out some facts about the answer, and then say, well, the analytic continuation, if we could do it, would have to give that answer, right? Because it has to give the right answer for the tensor network. So that means the answer in gravity also has to be the same answer that we found for the tensor. So this sort of feels like cheating and feels like we're somehow not using gravity at all, but we are. We're just using we're using the power of quantum information and quantum mechanics to do an analytic continuation for us that we otherwise couldn't. Okay. So when you do that, when you look at the tensor network things, you apply. These are exactly the questions that one-shot quantum Shannon theorists have been studying for the last decade or so. What you find is that you don't get the naive quantum extremal surface prescription. You get what we call a refined quantum extremal surface prescription. So the naive prescription would say that you just take the generalized entropy of the smaller quantum extremal surface, right? So a way to write that's maybe not the usual way, but works, is that you get the area A1 plus the sort of the entanglement entropy of B and B prime if the conditional von Neumann entropy of little b prime conditioned on little b is less than the difference between the two areas A2 and A1. Okay, that's just a rewriting of this quantity being smaller than this quantity. But we're going to write it that way because it's going to generalize to the refined prescription much better. And similarly, if the conditional von Neumann entropy is bigger than the area difference, then we get A2 plus S of little b. Okay, so a refined version, which just comes to the tensor networks and seeing that has to be equal to the fixed area states in gravity, is that we get, we get the right naive answer of area 1 plus the von Neumann entropy of little b and little b prime. Not if the conditional von Neumann entropy is smaller than the area difference, but if the conditional smooth max entropy is less than the area difference. And similarly, we get A2 plus S of little b if the conditional smooth min entropy is bigger than the area difference. But there can be an intermediate regime where the min entropy is smaller than the area difference, but the max one is bigger. And in that case, you get something that's smaller than either of these things, but it's more complicated than just some generalized entropy. You get large corrections to the naive quantum extremal surface prescription.
I'm sorry, Geoff, if I missed it, but can you say a little bit about the difference between the min and max versions of this entropy?
So the smooth max entropy without any conditional stuff, right? The smooth max entropy was like the log of the rank in a state that was an approximation of our original state, right? The smooth min entropy is minus the log of the largest eigenvalue in the approximation of the original state. So rather than being about the size of the sort of smallest eigenvalues that you can't throw away without changing the states too much, it's the size of the largest eigenvalues that you can't throw away without changing the state too much. So the conditional versions are much less intuitive, but the best intuition I can give you without, like, I could write down the formal definition for you, but it would not help you at all. The best intuition I can give you that I will explain more in a bit is that roughly, so the smooth max entropy is, if I want to compress a quantum state, then the number of qubits I need to compress it, if I allow myself some error epsilon, is the smooth max entropy, right? The conditional smooth max entropy is the number of qubits I need to communicate little b prime, the state on little b prime to someone who already has access to the state on little b. So having the state on little b can help them. And so that's why this thing can be sort of smaller, just like the conditional von Neumann entropy can be smaller than the ordinary von Neumann entropy. But yeah, that's really the best intuition I have. The best way to think about the conditional min entropy is that for a pure state, then the conditional min entropy of little b prime conditioned on little b is the conditional max entropy of little b prime conditioned on little b bar. So that should at least make it clear why you have this sort of symmetry between, you know, for one of the surfaces, you have the max entropy of little b prime conditioned on little b, and for the other, you have the min entropy. It's because this is really the minus the max entropy of little b prime conditioned on little b bar, and you know, so I can multiply this whole equation by -1, and I just get this equation except with little b replaced by little b bar, and a2 and a1 switched around. So that's why this thing is symmetrical, and you know, if I get the same answer for big B and for big B bar for a pure state. Yeah,
Geoff,
yep.
Yeah, is the intuition more or less right that the following one? If you think about spectrum of the density of the eigenvalues of rho, and then there is a gap in general, right? If you superpose two different things or mix two different things, and then the jump of the entropy by phase transition is much smaller than this gap. You can't say it's one is dominating the other. I mean, it's just
that's exactly the right intuition for the simple case where you have a mixture of
simple case,
things. And for the non-conditional smooth max and min max entropies, what they're really telling you is that they're telling you sort of the range of eigenvalues that matter for the density matrix, right? Like the von Neumann entropy of a density matrix is telling you the sort of mean log eigenvalue of that density matrix, right? These smooth min and max entropies are telling you sort of upper confidence bounds and lower confidence bounds on the log of the eigenvalue, right? It's telling you that the probability that you picked an eigenvalue that has log lambda, log 1 over lambda bigger than the smooth max entropy is smaller than epsilon. Similarly, that you got something smaller than the min entropy is also smaller than epsilon. Unfortunately, these conditional, one thing I should say is these conditional min and max entropies are not, the von Neumann conditional von Neumann entropy is just a difference between two von Neumann entropies, right? So you might hope that these conditional min and max entropies are just, again, difference between, it's like H max B prime B minus H max B. But that's just not true. There are certain inequalities that relate them to differences, but in general, they're just a new thing. And it's a very unintuitive thing, to be honest. Like the intuition I can give you is this thing, but as I'll explain in a minute, that's really just equivalent to saying that in a tensor network, this is the thing that controls whether all the information from little b prime gets through to little b. That's really the best I can do. Yeah. So the final thing I want to say about this general rule, and then I'll talk a bit about entanglement wedge reconstruction, and hopefully give some more intuition for what these things are telling us, is, so far I was just talking about fixed area states. For non-fixed area states, then the geometries get back reacted, and just even the geometries are hard to find, let alone analytically continuing the sum. But the neat thing is that we can write a sort of general semi-classical holographic state as just a superposition of polynomially many fixed area states, right? We just, if I have any operator, then I can expand any state in terms of eigenvalues of that operator, and I'm just going to do that for the area operator. And by very similar arguments to the one I made earlier about how the entropy of the mixture had to be the expectation of the entropies of the two states in the mixture, then we find that a leading order at least the entropy of the semi-classical state is just given by the expectation of entropies over the states in the superposition of fixed area states. So that means that at least at leading order, then we get the same answer for sort of ordinary semi-classical holographic states like the vacuum or just vacuum plus matter without any areas being fixed as we did for the fixed area states. So this isn't some weird fact about fixed area states. It's a very general set of facts about how the quantum extremal surface description works. Okay, so last thing I want to talk about is what this has to do with entanglement wedge reconstruction and sort of how it connects. Entanglement wedge reconstruction is really going to connect us to sort of this thing quantum state merging, which is the main operational definition of the smooth max. So hopefully I might clarify some intuition. So what is entanglement wedge reconstruction? It's the claim that everything between the minimal quantum extremal surface and the boundary is encoded in that region. Okay, so more formally, any operator on the bulk, I can find an operator on the boundary that does the same thing. So as Almiri, Dong, and Hollow pointed out back in 2014, this can't really make sense as a statement about bulk operator that works on all the states in the Hilbert space. Really, the right thing to be thinking about is operator that acts only on a code subspace of states that have this particular geometry. And so we can meaningfully talk about the bulk operator. And then the boundary operator only has to do the right thing on those code subspace of states. If we're thinking about a particular density matrix rather than sort of a particular code subspace of states, then really a more precise thing to demand is that the bulk operator, we find a boundary representation of the bulk operator that has the correct action on a purification of that bulk density matrix. So if we took the bulk state to be maximally mixed on some code space, then this is really the same definition we had before. It has to do the right thing on all states in the code space. But if we have some particular state rho that maybe isn't maximally mixed, maybe has some entanglement between the different regions, then the natural sort of question to ask about whether the entanglement wedge is reconstructible for that state is whether we can find a boundary operator that does the right thing on a purification of that state. Okay. And for that precise definition of entanglement wedge reconstruction, then what we find is that the condition for being able to reconstruct little b prime on big B is exactly the same condition you need for the quantum extremal surface prescription to apply to the state rho, namely that this smooth conditional max entropy is smaller than the difference between the two areas. Okay. So how does this connect to quantum state merging, specifically what's called one-shot quantum state merging? Well, one-shot quantum state merging is the following sort of quantum information task. Okay, so what you do is you say, we start with a situation where Alice and Bob share some state rho AB. So let's imagine that's a mixed state rho AB that's like purified by some third system that neither of them have, or at least neither of them are going to touch. Now what they want to do is they want to transfer Alice's part of rho AB to Bob by sending as few qubits as possible. There's little quantum communication as they can get away with. Okay, so that at the end of the day, Bob is just going to end up with a state that he has entirely that is going to sort of purify the purification of rho AB. Okay, so he now has rho AB, this reasonably strong sense of the word. The key point is that this is really just the sort of Schrodinger picture version of entanglement wedge reconstruction. So if Bob is an observer with access to the boundary region big B, then he sort of already has access to region little b, because that's easy for him to get. That he has that no matter what the entanglement wedge is. And he wants to learn about this region little b prime. And what he gets is he gets some information about it. He gets some sort of noisy version of it that sort of makes it through the extremal surface. So the question of whether he can reconstruct the stuff in little b prime is exactly the same question as whether he can reconstruct Alice's part of the state from getting sent some qubits that are sort of a noisy encoding of Alice's part of the state. And it turns out that the smallest number of qubits that you need to send, like if you use the best encoding, the best sort of noisy way to encode Alice's part of the state as possible, the minimum number of qubits you need is exactly this conditional smooth max entropy. So what's happening, you can show that the maximum number of qubits from region little b prime that you can learn about using region big B is exactly the difference between the two areas. So what's happening is that gravity is sort of doing one-shot quantum state merging as efficiently as it possibly can. So yeah, that's kind of cool. It's, there's a lot of examples like this, right? Of black holes being the fastest quantum computers. Black holes, like gravity saturates a lot of bounds. This is yet another one it does. But I've sort of been hiding a key point in my description so far, which is I was careful to say that they were wanting to use as little quantum communication as possible. To actually achieve this in one-shot quantum state merging, you need to assume that you can send as much classical information from Alice to Bob as you like, right? So you can like do measurements on Alice's part of the state and then send the measurement outcome from Alice to Bob. So actually, in fact, this is pretty key for it to this answer to make any sense, because this conditional smooth max entropy, and the conditional von Neumann entropy can be negative, right? If the two states are highly entangled, it can be negative. So how can you have to send a negative number of qubits from Alice to Bob? Well, the answer is that if I have a load of entanglement and I can send classical information from Alice to Bob, then I can do quantum teleportation. So actually having this shared state rho AB, not only can you send it over to Bob without doing any quantum communication, you can actually also end up with some extra ability to do teleportation. So you sort of end up with more ability to send qubits from Alice to Bob than you started with. So anyway, that's sort of an aside. But the key point is that the amount of classical information that gets from in gravity from region little b prime to the boundary region big B is not any bigger than the number of qubits that gets there. There's no extra classical information that gets through. So this was proved by Ning and Hiroshi Oguri just by computing the Halevo information, which bounds the amount of classical information that can be transmitted. So you don't actually have this sort of ability to send extra classical information from Alice to Bob. So, what the hell is going on here? Why are we getting this answer that is only possible, supposedly, if you can send all this extra classical information when we can't even send any classical information? So is quantum gravity doing magic? The answer is no. So what gravity does give you is it gives you what's called extra 0-bit information being transmitted from region little b prime to region big B. So this was discussed in a paper I wrote with Patrick, my advisor, 2018. But again, I'm not going to try and explain it because I'll just end up confusing people with the time I have. But the key point is that this is like it's a communication resource that is less useful than classical information. If you have the choice, you should always take the classical information. It's strictly more useful. but it's still sufficient to be able to do state merging with this number of qubits. So this is why gravity has just enough. 0 bits are really the minimal thing you need to be able to do state merging. So gravity is really giving you just enough capacity to be able to have this make sense. And that's, it uses that minimal capacity to make everything work out, to be able to communicate the information it wants from little b prime to big B.
I'm not sure this is a well-defined question, but I'll ask it anyway. This ability to get away with the 0 bits rather than classical information, is that universal, or is that happening here because there's some special structure to the states that we're considering?
Yeah, no, this is universal. So ordinary quantum state merging using classical bits is sort of unnecessarily inefficient. And yeah, so the same thing is true for quantum teleportation, right? Quantum teleportation, the normal way you do it is you share some entanglement and then you send some classical information. Yeah, that classical information plus the entanglement lets you send quantum information, but you don't actually need to send the classical information. You just need to send 0 bits. That's like a weaker thing that is still sufficient to do teleportation. And exactly the same thing is true here. That there's a resource inequality called fully quantum Slepian Wolf, and that can be converted into quantum state merging, but it can also be converted more efficiently into quantum state merging, except using 0 bits rather than classical bits. So yeah, this is not specific to anything about gravity. This is completely general state. Okay, so just want to make some final comments because I've run a bit over in terms of time. So what should we take away from this? Well, the first thing is that the replica trick in gravity is like, it knows the quantum extremal surface prescription, which is really, really cool. That knows an awful lot already, but it knows even more than that, right? There's questions that the quantum extremal surface prescription sort of naively wants to give the wrong answer to, but the replica trick still knows to give the right answer. It's also kind of nice because there was a weird oddity from a quantum information point of view, in that holography only involves a single state, right? And in quantum Shannon theory, in quantum information theory, von Neumann entropies only play an important operational role, with very minor exceptions, when you have a large number of copies of the same state. So say you have some density matrix rho, and then you look at rho tensor product at n and n times, and then take the limit n to infinity. It's called the IID, asymptotic IID limit. That's really the only times that von Neumann entropys actually matter. And yet, for things like whether entanglement wedge reconstruction was possible and stuff like that, in holography, von Neumann entropys seem to be the thing that was playing the crucial role, right? So the sort of lesson of this paper is that the reality is it was always the smooth max and min entropies that were actually what mattered, which is good because these are the things that matter in like one-shot quantum Shannon theory when you only have a single copy of the state. So everything makes sense from a quantum information perspective. It just so happened that the states we were typically considering were sort of nicely compressible states where these smooth min and max entropies and all these more complicated one-shot quantum Shannon theory things were basically equal to the von Neumann entropy. So we could get away with just considering the von Neumann. So yeah, that's all I have. Yeah, I'm sorry. It's sort of it's a paper where there is a lot of stuff we covered and it involves a lot of background in a variety of fields. So I apologize for not being able to sort of glossing over explanations of things. But hopefully I gave enough to give a vague intuition for how the sort of story works and how the roles these different quantities play. So yeah, thanks very much.
Questions?
Hey, Geoff. Hey, so I had a quick question.
Yep.
Is there some interesting classification, a set of information theoretic tasks for which a quantum side channel is necessary? Because like maybe there's some interesting statement that can be made about these are
You mean
classes
like
of tasks that can't have a holographic dual description because there is no classical side channel.
oh right, that a classical side channel is necessary, but a 0-bit side channel is insufficient.
That's right.
So the classical capacity. So there's things where you can, yeah, there's certainly things where classical communication is like harder to get than 0-bit communication. In gravity, for example, you can get less 0 bits, get more 0 bits through than you can get classical bits through, and that's pretty general. I can't think of anything where it's more useful than 0 bits. I mean, classical tasks, I guess. If you want to communicate classical information, right, then or if you want to like state merge some classical state, then it's more useful. But for things that are defined just in terms of a arbitrary quantum state, I can't think of anything. But yeah, I think that's an interesting question.
I guess the other question I had, which probably is pretty simple, is if the correct way to think about all of these RT surfaces is in terms of the smoothed entropies, they're actually giving you the leading order of the smoothed entropy instead of the leading order of the von Neumann entropy, then it seems to me that you have an even more striking restriction in the allowed kinds of entropies in terms of these smoothed entropies for holographic states than you do for von Neumann entropies, because my impression for these smoothed entropies is that their constraints are very poorly understood.
You mean inequalities that they satisfy?
Yeah.
Generally, I think the smoothed entropies tend to satisfy, like they satisfy more than something like a Rainy entropy. But they satisfy weaker things than the von Neumann entropy. Von Neumann entropy satisfies like a lot of inequalities and has a lot of nice properties. And I generally these things don't satisfy as much as that.
I guess what I'm saying is holographic.
One comment I should make that's maybe relevant to your question is that sort of I only talked about calculating boundary von Neumann entropes in this talk, right? And I guess entanglement wedge reconstruction, which is just a very general, not a specific quantity. You could also calculate boundary smooth max entropies and stuff, and yeah, it would like for the boundary von Neumann entropy, the smooth min and max entropy is only mattered in terms of the conditions for which rule to use, right? If I look at this description, then it's still an ordinary von Neumann entropy that appears here. If I was computing, say, a boundary smooth min or max entropy, then it would be presumably a bulk smooth min or max entropy that appears here. So that's, yeah. Yeah, one other comment is that yeah, the generalized entropy is a usually finite quantity, unlike the two constituent components. And so presumably we want, we want the two sides of this. We want the two sides of this to either have no divergences or have the same divergence. And the divergence of this conditional max entropy, the leading divergence, will be the same as the divergence of the von Neumann entropy, but there will be subleading divergences that will be different. So I think actually the right thing we should be looking at is this conditional entropy versus the sort of it shouldn't be versus the expected value of these areas. It should be the expected value plus some fluctuation, where you know, the size of the fluctuation is again controlled by epsilon. So presumably the sum of like difference in areas plus conditional smooth max or min entropy, once we take into account those fluctuations, should be renormalizable and UV finite. And there's some evidence that this is true, but I don't think we have like, yeah, there's certainly a lot more evidence for the ordinary generalized entropy than there is for that. I think it's a very interesting open question.
Hey, is it fair to say that the duality is kind of duality between resolvent and the gravitational path integral, no matter what quantity you want to compute in the end with it?
Yeah, sure. Yeah.
Okay.
Though one thing that's true is I don't know what the resolvent is for a general bulk state.
Yeah, because it's hard to.
So I guess the prescription is that in this top case, then the resolvent looks like the resolvent. You know, it looks like it's tightly peaked about e to the minus a. Yeah, it's tightly peaked about e to the minus a1 times like your bulk density matrix. And similarly for this one, we know what the resolvent is, and for this case, then the resolvent is just something more complicated. Yeah, I think that's a completely fair thing to say. And then the Von-Neumann entropy is just a particular measure of what the result.
Yeah, in certain cases simplifies, in certain cases some simple quantities enough to get.
Exactly.
So very, very long time ago, when I was thinking about resolvents, I thought about them in two different ways. One is quite literally as finding a saddle point of something, like the matrix integral. And the other is as sort of describing some emergent geometry. Do you see it that way? I mean, the first one is perhaps obvious, but the second, I mean.
Yeah, you're thinking in some sort of, you're thinking in like a random matrix theory where like the emergent geometry on the world sheet or something like that. Yeah. Yeah, good question. I don't know that story particularly well, and maybe if it may be worth me thinking about that story more and seeing if there's some way it naturally fits in. Off the top of my head, I don't see how, but yeah.
So these matrix integrals are supposed to describe these restricted classes of states, these fixed area states. Is that what I'm understanding?
Yes, roughly speaking. I mean, we're never directly using a. Well, I guess we're sort of using the tensor network is sort of a matrix integral, right? Because it's a random state. So we can think of that as basically a random matrix integral. But the resolvent we're getting from a gravity point of view, we're getting this resolvent just by doing the gravity replica trick, and we're not we're not directly plugging in anything involving random matrices. We're just using tools that were developed for them. Yeah. So yeah, it's a very good question. I should think about it more, but I don't have anything to do right now.
Yeah, can you tell me about your gravitational path integral? What sort of saddles are you summing up? It's not just a sum of two saddles, right?
Yeah. So it's. Let me just go back here. So the saddles we're including are so we have fixed area states, right? So we can have conical singularities at any of these surfaces, and we're having sort of n copies, okay? And we're considering so we're having n copies of the unback reacted geometry, and we're just gluing the different parts of the bulk together. So sort of this region here just gets glued onto the corresponding bra, okay? And this region here gets glued onto the corresponding bra one sheet over, one copy around the cycle. And then finally, this central region gets glued onto the corresponding bra, where you apply the permutation pi. Okay, and pi is, we're going to consider saddles with summing over all saddles with different permutations pi, where pi is a non-crossing permutation. And then we're taking the sum over all that saddles, and then that is what we're analytically continuing. Although we're not directly doing the analytic continuation, we're using these results to get the resolvent, and then using the resolvent to get the one line. Is that clear?
I have a question about your analytic continuation.
Yep.
Can you interpret it as, in terms of other ways of analytically continuing SN, like Deligne categories? Analytically continuing the representation theory of SN?
That's a good question. Again, I don't know the literature on that well. You said it's Deligne categories. Is it? Yeah, I don't know really anything about them. So it is entirely possible. I'd love to talk to you about that afterwards, potentially, in terms of what can be said.
That might be fun.
Yeah.
Actually, I have another slightly quick question.
Yep.
If we wanted to avoid having to think about one-shot entropy, what's stopping us from thinking about many copies of the holographic state?
Good. So, I think the point is, even if I look at, hang on, let me think about this. Yeah, so even if I look at many copies of the holographic state, then it still won't just end up looking like von Neumann entropes, because what's the right way? Here's the right statement. If I looked at I would need to apply some random unitary to the bulk states on all the many copies that sort of mixes all the states on the many copies together. And then if I did that and then looked at the boundary states, then I would always end up with, I could forget about smooth minimax entities, I think. But if I just take many copies of the bulk state, but the bulk state itself is like, some mixture of two very different things or something, then I don't have any law of large numbers in how that bulk state gets mapped to the boundary, right? I'm then looking at a large number of boundary states, but that doesn't help me at all. I feel that explanation wasn't as satisfying as I could have made it, but yeah, really.
Is it fair to say that the factorization just doesn't continue into the bulk? It looks like on the boundary, you're just having n copies and it's a fairly trivial system, but the bulk connects them?
No, the bulk will be just n copies and it will be a trivial system, but you need to, so the law of large numbers applies when I take the n copies and I do something random to them. So let me give a better example. If I want to compress the n copies of the state rho, right? I can't just compress each copy individually. I have to take all the copies together and then do like a correlated compression. It's not really an entangled compression, but it's a correlated compression where I say, I only take I assume that if I just think of classical distributions, right? Let's say I had 0 with probability 9/10 and 1 with probability 1/10. Okay, and now I sample from that distribution 1,000,000 times. Then what I can say is, oh, it's definitely going to be that 100,000 of them will be 1 and 900,000 will be 0. So I just need to tell you which 100,000 were 1, and that's enough information to communicate the state, right? But if I have to tell you first about the first 1 or 0, then about the second 1 or 0, then about the third 1 or 0, then I can't do that, because I just have to tell you whether each one is 1 or 0. I can't take advantage of the law of large numbers to do a compression. Same thing is really happening when I look at lots of copies of the state in ADS-CFT.
I think I was just asking if you did have n copies and you wanted to compute the entropy of some, union of all the regions B in every one of these copies, would you not have bulk in the bulk path integral? Would you not have contributions that connect the different bulks?
Yes, but I think they'd be very suppressed.
Oh, okay.
Because you wouldn't have any. If I just take some multiple copies of the same state, yeah, and they're not. There's nothing coupling together at all. Then wormhole contributions are going to be very suppressed. This is not like sort of replica wormholes or something, because in replica wormholes, then you're swapping in replica wormholes. You're like gluing together the different copies of the external reference system, and that's what enhances the wormholes relative to the non-wormhole contribution. If I just imagine I looked at like the entropy of the black hole and the Hawking radiation, that's just going to be 0, and it will. If I do the replica trick, the contributions from replica wormholes will be. I mean, they won't exist. There won't be saddle points, but even if there were, then they'd be very, very suppressed. Yeah. Is that clear?
Thanks.
Any more questions? No? Okay, let's thank Geoff again.
Excellent.